Good morning, guys, and welcome to week 7 of Astronomy 120. This is the late start class. So today is actually October 17th, and we're continuing actually with the solar system. We still have 3 units of the solar system, 2 of which we're covering this week. 1 more unit is going to be next week, and we will be done basically by the for the solar system. So actually, probably 2 more units after this week's unit. So for a total of 4 more units. So we're in the mix of everything. So we talked about the Earth as a planet. Then we went into the Moon, which is the next closest object to us after Earth, of course, in terms of our capability of the studying. Then we chose Venus for reasons that I outlined before. And now we're moving to the outer planets. Specifically, we're going to look at the 2 gas giants, especially Jupiter. We're going to actually also explore Saturn. And this does not really exclude the other 2 big ones, namely Uranus and Neptune. And Uranus and Neptune have a very, very interesting story on their own. First of all, their discovery itself is a story, especially that of Neptune, because Neptune was discovered by pure mathematics, which is really something amazing in a sense that, hey, you go and work out the path of Uranus, which was discovered by Herschel, actually, in the mid-1800s. Then you work out the path of Uranus, and you discover that, hey, there must be something out there of this specific size and this specific location to alter the path of Uranus to this way. So that's what 2 independent, basically observers, basically mathematicians, after they got the data for Uranus, they went in and they said, okay, there must be an object in that location of the place. Okay. Well, the German Astronomical Society basically pointed the telescopes in that specific location and found Neptune. That's how Neptune was discovered, which is really an interesting topic by itself. Then later on, of course, the same idea was repeated for the case of the path of Neptune also, that seems to be altered enough, at least for the original observations. And the hunt for planet 9 was triggered by that same reasoning. Basically, based on observations, you make calculations, and based on the calculations, you say, okay, there must be an object in there. And then when it was found, they thought, okay, we have found it. That's where Pluto was discovered. Pluto turned out to not meet those specifications in a sense that its mass was too small for the predicted values. So there must be something wrong, and indeed it was. What was wrong in that case was the math in that case was based on data that was misinterpreted. So in other words, even by accident, using mathematics, we were able to discover Pluto. So that's the extent with which, at least that discussion is interesting. That's not the end of it, actually. As recent as 4 years ago or so, it's about 2015, I don't know, yeah, about several years ago, there was a big announcement of another planet that must be more massive than the Earth also out there, based on the observations for a lot of objects that are past Neptune, called TNOs, trans-Neptunian objects. And this includes among other things. Of course, now Pluto is one of them, but there were other also objects in there that are a little bit smaller than the big ones, smaller than Pluto and Eris and Makemake and Quaoar and Sedna and all of the other objects in there. And those objects seem to have kind of convergence to a specific point and then divergence from it. In other words, their paths seem to have suggest the existence of another planet. Based on their orbits, you can estimate the size of that object, and that is where planet 9 is right now. So there is a big hunt for planet 9 based on, again, the mathematics. So it's an interesting story for the case of Uranus and Neptune that we're actually excluding today because of the fact, again, that we don't have enough weeks to cover everything in here. So the focus is on these 2, namely Jupiter and Saturn. they're actually a big part of the solar system. As a matter of fact, Jupiter is probably the dominant player in the solar system. If it were not for Jupiter, probably life as we know it on Earth would not have existed, because Jupiter acts as a shield for all of the inner planets, and it protected them from the influx of all of those comets and those asteroids that are bound to hit them, but instead they find this big, massive object that sits right in the middle of the solar system and plays two roles: either attracts those objects or divert them outside. So Jupiter played a major role for life to evolve on Earth as we know it, and probably also protected a lot of the inner planets. That's why the thinking now is, if you were to find life outside of the solar system, basically, you really need to have, yes, you have to have a planet that sits in the so-called Goldilocks zone, in a sense that it has liquid water on its surface, in addition to the other two phases, namely gas and solid, ice. And also all of the temperature, modern temperatures and everything else, and its weather is more or less regulated and everything else. But you also need some big protection shield, like the one that we have in here for the case of the solar system, namely Jupiter. So Jupiter plays a major role in that, okay, for the case of the solar system, and it is the biggest planet, okay. So the name Jupiter, which stands for the king of gods, is probably, at least in a sense of the sizes of the planets, can be justified in this sense. It's the biggest planet in the solar system. As a matter of fact, when the solar system started to form, obviously, when we discuss the formation of the solar system, basically as the cloud starts to concentrate more or less, for the most part, it went to the center, and that's where the sun was formed. But then immediately after the sun started to form, also Jupiter starts to form. So Jupiter was the first planet to start to form, and as it started to grow, it gathered more and more material, just like the sun was doing, okay? The only trouble is it started a little later than the sun. So it gathered a lot of those gas and dust that was in there, namely the two main components are actually hydrogen and helium. And then later on, Saturn probably started and the other planets started to form. Had the sun, because the sun now starts to basically compress, and as it compresses, its internal temperature starts to increase, just like Jupiter was doing, except Jupiter was a little later than every single state where the sun was. So the sun, inside of it, the temperature was so hot that nuclear fusion starts to happen and starts to radiate energy. That's basically what happened at that point. Those first blasts of solar winds drove most of the gases away, and in a sense starved the growth of the planets, especially that of Jupiter. In a sense, Jupiter could potentially have grown to be another star, but it did not have a chance because the sun went too soon and it's close enough from it. So material that was close to it, so that it gathers more of that hydrogen and helium to become a star, was gone for the most part, okay? So this is why sometimes when you're reading about Jupiter, you might see the reference that it's a failed star. So in a sense, it's a big enough planet, but it's too small to be a star. As a matter of fact, there is a limit on which a star forms, and it's usually measured in terms of how much Jupiter masses of we have, okay? And that is why the Jupiter is a big player. I mean, think about it for a second. If the sun did not go nuclear immediately, probably you could have two stars in here, which could be an interesting topic by itself. Albeit one star would be dominant, namely the sun, and the other star will be a super dim star, but it's still out there in the night sky. So this is the story of Jupiter. Jupiter is a big planet. It's about 5 astronomical units from the sun. Namely, it's about 5 times way from the sun as the Earth is. At some point, both of them will be on the same side, and the sun will be on the opposite. The Earth will be in between Jupiter and the sun. And the distance between the Earth and Jupiter is only about 4 astronomical units. On other times, the Earth will be on the opposite side of the sun, and Jupiter is in its orbit. So in this case, the sun will be between them. So you add 5 astronomical units from the sun to Jupiter, and add another astronomical unit for the Earth. Now you have a total of about 6 astronomical units. So the Earth at some points is about 6 astronomical units, and at some times it's about 4 astronomical units from the sun. We are in a time this year where we are actually about 4 astronomical units. Jupiter is its biggest angular size in its path. At some other points, it will be in the opposite direction. But frankly speaking, as you did, that was part of a homework assignment that you guys have, the calculations will make very, very tiny changes because we're talking about a huge distance. So going from a very small number to an even smaller number, both of them are almost of the same order of magnitude, will not make much difference in terms of the angular size. So the star slightly small and big is not, or a planet in this case. Okay. By the way, the word the planet, and we had that discussion a long time ago, this really means a star that moves around. Okay, so let me prepare the notes that we have to go through. And let me go into the objectives and let me share that with you guys. Share. Didn't I prepare it? Show more. Here it is. So again, Unit 45 deals with these 2 big planets. Okay, it's going to deal also with the main features of these planets, namely that you have a layered structure on their upper atmosphere. And we will try to dig inside, try to understand how they are structured. At this point, we really don't have a clear, actually, how should I put it, a picture of what's going on inside. We tried to dive into these planets. We sent probes. Cassini was the last one in 2017 that fell into actually Saturn. So after it did a big study of Saturn and its moon, especially Titan, the moon Titan, actually it sent a lander on Titan, namely Huygens, and then Cassini itself actually went into orbit and actually smashed into the planet. And it collected data before going into the planet. But because of this thick atmosphere that they have, thick gases that they have, Cassini burned before even it reaches even the lower, not even the lower, a little bit of the lower levels of that atmosphere because of that tremendous friction that it has with them. So it signals in the last few seconds of its life, basically sending us data. So in the last basically death stages of it, but it was really an interesting thing. So we don't have really a good, I should say, data for the internal of the planets, but we think that because of this several things. First of all, because of the force of gravity, we have an understanding of how that might go in a sense of compression of those gases to the point that they become liquid. What I'm talking about is hydrogen. Hydrogen in a liquid state is a very, very weird state. We don't have the likes of which in here on Earth. You need tremendous pressures to do that, to take hydrogen, which is a gas, the lightest gas, and compress to the point that it becomes a liquid. Why would we think that? Why do we think that we have liquid? First of all, like I said, tremendous pressures, and the planet is mainly hydrogen for all practical purposes. And the other thing also, the magnetic field. Those planets have tremendous amount of magnetic field, especially Jupiter has that. So how can we explain that? Tremendous amount of magnetic field on a planet that does not, for all practical purposes, has a core, basically a rocky core that we know of it. Although, according to the nebula theory, they must have some sort of they must have started at least with that structure to get more and more materials under to themselves. So in this case, the hydrogen liquid metallic hydrogen liquid, okay, could be the best explanation for the strength of that magnetic field, how strong it is. So think about it. Hydrogen is an element that sits the first elements in the periodic table. And it sits on the same side as the sodium and those potassium and all of those highly basically active minerals, okay? So it's behaving like them now. Behaving like those, meaning it's contributing when it's in liquid state, an electron outside that can freely move. And since the planets are spinning, and they're spinning actually fast, relatively speaking, faster than even Earth. A day on Jupiter lasts less half a day than Earth, less than 12 hours, 10 hours, okay? So they're spinning super fast on their axes, and they're big. Much, much bigger than the Earth. Take Jupiter, for example, it's about 11 times bigger than the Earth. How many Earths can I fit in Jupiter? Well, you do the math. It's not 11 for sure, because 11 is only on one axis, okay? But you have to think about the other axes too. So you have 3 axes, 11 times 11 times 11, that's more than 1,000 Earths can fit inside Jupiter. But the Earth being a little denser than Jupiter, not a little denser, a lot denser than Jupiter. Jupiter density is about 1.23, I'm sorry, kilogram per cubic meter versus that of the Earth, which is about 5.5 kilograms per liter. So the Earth is denser. So even though it's much, much bigger than the Earth, about 1,000 times bigger, its mass is only 300 times as big as that of the Earth, and the numbers fit. So this is in terms of that structure. Now, in terms of comparison between Jupiter and Saturn, the two are not really that big of a difference in terms of size. Yes, there is a difference. Jupiter is bigger, but it's more massive, Jupiter, far more massive. So for the case of Saturn, it's slightly less in size, but it's a lot less in mass. Which brings me to the point of its density. The density of Saturn is a lot less than that of Jupiter. So it's mainly gas that is basically floating, a lot less denser gas. As a matter of fact, its density is less than 1 kilogram per liter, that is. And why 1 matters? That's the density of water. So Saturn is less dense than water. So if you have an ocean big enough, and there is no ocean big enough on Earth, or at least that on the solar system, that you can put Saturn on, it's going to float because its density is less than that of the water, so it's going to stay on top, basically. So that is some of the interesting stuff in here, and this is the stuff that we're going to be exploring. One of the features that is actually we're going to explore is the so-called Great Red Spot. This has been noticed that it's an active hurricane or an active twister on the planet that seems to go forever. It has been first observed 300 years ago, and it's an ongoing event on the planet, on Jupiter, that is. You say, is this unique to Jupiter? The answer is no. What is it driven by? It's driven by the rotation of the planet and the gradient in temperatures and all of these things that are driving the weather phenomena on Earth, but they're in much, much larger scale than this on the case of Jupiter. Why? What's going on with the Saturn? Well, it has similar features, except that the scale is a lot less and the time scale is actually a lot less. So whereas the other one has 300 years and it's still an ongoing event, it's shrunk a little, but then it grows again. For the case of the other one, yes, it has also. We were able to observe them not just for the case of Saturn, but we were also observing it for the other 2 planets also, the ice giants also, being the Uranus and Saturn. So this is in a nutshell what the unit is all about. The next unit is going to focus more on the moons of this planet. Since we're going to be talking about the moons, there are 2 missions at least that are extremely exciting for the moons that are being explored. Actually, they are building the spacecraft for them to go to both Europa, And the mission for Europa is called JUICE, that is between NASA and ESA, the European Space Agency. And it's called JUICE, stands for Jupiter Ice Exploration, or Ice Moons Exploration, or something like that. And then you have the other one, the Dragonfly, called for Titan, the other mission also that is probably going to be launched in about 2 years from now, but it's not going to be there until like 1935 or 34 or something like that. 2034, 2035. So it's going to take a long time before it reaches there, because again, we're talking about Titan, the moon of Saturn, and the moon of Saturn probably. I mean, this is the exciting thing about these two moons, the reason why these two projects are important. There is a good potential for life on Europa. And the first mission, JUICE, basically will go by Europa, fly by it, and try to collect as much of the water that is coming up of the cryogenic volcanoes that are erupting on the surface, collect that water and analyze it for organic life. Okay, not organic molecules, organic life, basically try to find life on those things, because we believe that under the surface of Europa there is a salty ocean in there suitable for life as we know it. So probably we will be able to collect that, and if we don't find it, it's probably not part of the Egyptian materials, but probably life does not exist in there, and that raises a big question why that is. That is one thing. The other mission also is to Titan. The second one, the Dragonfly, is also going to Titan. We were able to discover a lot of things when Cassini sent its Huygens and that landed on Titan. And that is, there is a liquid cycle on the surface, albeit it's not that of the water as we know it. It has methane and also some organic, different kind of materials in there. And we were not sure when Huygens was sent if there was a liquid. I mean, if the planet is entirely thin, or the moon itself is entirely a liquid, I mean, in surface. So they were not sure. So they sent a probe so that it actually floats on the surface. But now we know there is a solid surface, because as Huygens landed, there was a solid surface, although the surface is completely different than that of the surface that we have it in here, in terms of it's an icy structure because of the cold temperatures. It has actually regular atmosphere. It has it has a regular pressure, I should say, in its atmosphere. So it has a lot of interesting things that we're exploring. There is all kinds of, there is a source of energy, there is carbon-based basically materials in there suitable for life. There is a liquid cycle in there on the planet, albeit it's not water. There is all kinds of conditions that are suitable for life, but not necessarily that of the life as we know it on Earth. In other words, a way of making energy and growing and things like that. So there is actually a good chance also that there is a non-carbon, at least non-Earth-like form of life, at least on the moon Titan. And that is actually the second mission, trying to go and explore it and find it. And again, it will be a very exciting day when we discover that. But it will be also a very exciting day if we don't discover it, because then it raises the possibility of why is life has evolved on Earth when the conditions were suitable, and it did not evolve, at least in the other two places where it was possible too. So this is some of the interesting things that are going on right now. Part of the objectives of this class is to be able to get you guys to be able to, when you read stuff like this one in the news or watch it somewhere else or something, you'll be able to understand what's going on and get at least involved with it, hopefully more than if you're not actually taking this class. Again, so these are some of the facts about the planets. Jupiter is about 5 astronomical units. It's about 11 times the size of the Earth. If you take 11 Earths, they will span the axis of the planet, namely the diameter of the planet. On each direction, it doesn't matter which direction you go. So that's why you have 1,000 times 10 times 10 times 10, which is 1,000. Okay, not 1,000 times 1,000. Okay, so about 1,000 times. What did I say in here? Yeah, I'm sorry. You take 10 planets, 11 planets, and you line them up, 11 and you line them up, and 11 you line them up, 10, 11 or 10 times 10 times is about 1,000, okay? And then the mass of the planet is not 1,000 times the mass of the Earth, because if it were 1,000 times the mass of the Earth and divided by 1,000 times the volume of the Earth, then in this case the densities will be the same. It's going to be a rocky planet, but it's not. It's less mass, so its density is a lot less than that of the Earth, slightly less than a third that of the Earth. Okay. So that corresponds to a different structure, namely it's mainly gas, albeit at some points it's denser gas. Okay. In terms of Saturn, it's further away. It's almost twice as far away from the sun as Jupiter is. Think about it for a second. You travel a long time from the sun to get to the Earth, which is 1 astronomical units. Then you just hop the next hop, which is a time and a half, you get into Mars. And then you have to go 5 times as far to get to Jupiter. By then, you have traveled long time, millions of miles, just to get to Jupiter. And that is not enough. You have to go as much as you did from the sun to Jupiter, from the sun to Saturn. Still very far away in here object. Okay. In terms of density, this is even less dense because the size is actually slightly less. So when you divide by slightly less, it's going to be slightly more actually than that of Jupiter, but its mass is a lot less. As a matter of fact, as I was talking about the density, it's less than that of the water. So that means Saturn would float in case if you put it on an ocean big enough to contain it. In terms of the structures, and this is similar to them, except it's more exaggerated for the case of Jupiter than that of Saturn, in the sense that these features are a little bit not that clear for the case of Saturn than the case of Jupiter. And this is this different zones that are forming in here. So you have a zone in here, and you have these belts in here, darker belts and lighter zones, and there is some of the spots that form in here, kind of like the great red spot for the case of Jupiter. Remember, if you were outside looking at Jupiter at any given night and you have a filter good enough to basically dissolve these colors for you, you should be able to see this red spot. If you see it, it's going to be moving because the planet itself is spinning super fast, spending about 10 hours on its axis. So on a given night, on a winter night, you should be able to see the entire planet basically going around its axis, okay? Especially if you are up in the northern hemisphere, you should be able to see the whole thing going around your eye from start to come back to a full circle, okay? Obviously in the summer, because of the shortened nights, this is going to be hard to do, okay? Unless you live in the southern hemisphere, very far down southern helisphere. Again, in terms of structure, it's 90% hydrogen. For the most part, it's hydrogen. This is H2, which is the hydrogen gas, and about 10% helium. And there are traces of other elements. Actually, the other elements, the traces of them, methane, ammonia, and water, are the ones that are giving it these colors. Methane has this orangey color, okay, and ammonia has this orangey color, and water is this surface, the white color. As these surfaces are basically flowing into one another, the lower layers are actually seen, and you see this different color. So this is convection as it's going around, and as it does, the inner parts are actually showing, okay? That's why you see these different colors. As I was saying, the bands for the case of Jupiter are not that distinct, but there are definitely bands in this structure, okay? One of the interesting things, and that came in an article that was published not too long ago, about the temperature of this Jupiter. The temperature of Jupiter is about what, 160 Kelvin on general, which is super cold, okay? Remember, right now, as we're sitting today, the temperature, I don't know, my phone is on the, so it's about 300 Kelvin, really. And this number is 160 Kelvin, is less than that, super cold, okay? But at times, it gets super hot also on the surface. So there was a mystery in here. What's going on? It turns out that there are auroras on the surface of the planet, and those auroras are coming from not from the gas that is coming from the sun, not from the fast particles moving from the sun, as much as it's coming from the moon Io, actually. And the moon Io basically is sending a lot of charged particles, and those charged particles hit the atmosphere of the northern and southern hemisphere, and that spreads all of the materials throughout the planet, heating the surface albeit for a short while. But the temperature at some points it's hotter even than Venus. Okay, that's at least according to the article. Anyway, this is the case of Saturn. Saturn is a little colder. It has actually more hydrogen than helium for its case than actually what Jupiter does. I mean, what Jupiter did. And it has traces of hydrogen-rich compounds, basically like methane and ammonia and all of the other materials. And its temperature on the outside is about 130 Kelvin. Don't be fooled by these numbers. In the inside, they're extremely hot. The rotation here takes about 10.7 hours, or 10 hours and 45 minutes, or 43 minutes to be more specific. This one takes less than 10 hours, 9 hours and 54 minutes. Okay, almost 10 hours. Okay, this is basically what we think their inside structure is. First of all, because of the force of the gravity, if you take a gas and if there is no gravity, it's going to uniformly spread all the way through it. But if there is a gravity, the upper part will press more and more, and the lower part, because they're going to fall in here, and of course the lower part will be compressed than the higher part, and this is basically what we think going on in here. Yes, they are mainly gas, but that gas has this structure in here in some sort of a layered structure, and both of them do have that. So we think that the inside, and there is no evidence for it in here, is made out of rock, and basically that's how planetism was formed for all of them. And they must have started like this too. And they have water in here in their surface, and the reason it has to be water is because the temperatures are hot in this case, okay, because of the compression, because of this process. And then there is a big layer of a metallic hydrogen. That's the one I was talking about to explain their magnetic properties, okay? And then the rest of the gases, and as you go up, you're going to have the regular molecular gases, meaning they're neutral, no charges, no nothing. So the interior of the gas giants, again, the density is about 1.3 kilogram per liter. The density of Saturn is less than 1 kilogram per liter. So because of the way the densities are, that explains their structure, okay? And there is a force in here to balance the two, because why wouldn't gravity keep on pressuring them so that the whole thing basically becomes as small as possible? Well, in this case, there is actually one big reason for this case, okay? Because for a case of planet or even a neutron star, there is other processes that are involved. For this case, if you take a gas, for example, and you compress it and the pressure increases, there is a law. Can you draw in here? Draw. Put this pen in here. There is a law that is known for a gas, for example. If you increase its pressure, the temperature increases accordingly. This is the so-called ideal gas law. So if the pressure goes up, the temperature goes up. Okay. And if the temperature goes up, so as the pressure goes up. Okay. This is an outward pressure. So think about it. Because of this, the material is trying to compress more and more because the gravity is pushing it more and more toward its center. Well, because you're losing, in this case, potential energy and converting it into kinetic energy, so the temperature increases. And as the temperature increases, the pressure increases. PV equal nRT, by the way, is the same thing that is responsible for a balloon to blow up. So if you keep on increasing, the volume in this case starts to increase, but not as much as the pressure that is increasing inside. So now the pressure becomes too much. So this is a well-known law. Okay, this is called the ideal gas law. So in this case, as the temperature increases, so is the outward pressure. But there is an inward push from gravity trying to compress the material. So once you reach that equilibrium, where the two cancel, so you reach the ideal size for that planet. That depends on how much stuff you start with, of course. Okay. Interesting fact about this thing is that if you pile up more mass, for the case of Jupiter, for example, if you pile up more mass, instead of increasing the size as much as you pile up, it actually shrinks in size. Okay, that's why some of the dwarf red stars, they're actually smaller in size than Jupiter. So Jupiter is actually a big size. It's actually a limit for a size of this material. Okay, the reason why the sun is bigger is because it has far more. That's why the density inside of the sun is even higher. Okay, so that's really the mass of the sun is about 1,000 times bigger than Jupiter. So no comparisons in here. Okay, and the volume, I mean the radius is about 10 times bigger. Okay, the sun's radius is about 700,000 kilometers, whereas the radius of Jupiter is about 70,000 kilometers. Okay, the radius of the Earth, just to give you an idea, is about 6,400. That's why it's 11 times less than that of Jupiter. To give you a sense of proportionality in here. So again, all of the structure is explained beautifully, and there is a comparison one-to-one. By the way, this holds discussions, and I know I made big fuss over this, and you guys know about it, that you're not supposed to skip the reading of these units. They are actually essential for your classes in here, especially for your exams and so on and so forth. Okay, in terms of the winds, as I was saying, the planets are spinning super fast on their axis. This generates all kinds of winds in here. This generates all kinds of vortices that form on the atmosphere, and this is basically the origin of all of those phenomena on their atmosphere, including the Great Red Spot. Okay, there is something in here about the Coriolis Force. If you were to go to the bathroom and flush the toilet, you will notice that the toilet will spiral, I mean the water in the toilet will spiral inward until it falls in. It's always spiraling in the same direction. So what's the cause of that? It is what is known as the Coriolis Force. Coriolis Force is similar to the force when you're sitting in your car and somebody starts the car. Your body tends to move backward. That is actually an inertia in reaction to the move forward. Or if you're moving and then somebody hits the brakes, your body tends to move forward. Again, that's inertia, trying to keep up with the initial motion until it's retained backward. Or trying to go on a curve. If you're going on a curve, you'll find your body moving in the opposite direction to which way you're curving, going one way or the other. So these are inertial forces. They are response of masses to the changes in motion. This is in the same thing, the Coriolis Force. Coriolis Force has to do with a spherical object, in this case spinning, and another object moving on its axis, moving up and down around it. And that is exactly what the atmosphere is doing as the planet is spinning. So that is actually an inertial force. It's not a real force in a sense, like, for example, the force of gravity or the force of magnetic force, for example, or electric force. So the Coriolis force is of the same classification as the inertial forces that I was describing in here. This has to do with a large body, like, I mean, any body actually that is spinning, and you have an object that's moving on its surface, it's going to experience this. Remember, the planet is spinning, and you have gases that are moving, so they're going to experience this force, and that is what the spiraling effect on the case of Jupiter is. And this is exactly the same reason also you have hurricanes and you have weather on the Earth with this intensity, like Hurricane Ian that hit Florida recently, or any hurricane that hits the northern hemisphere, it's spiraling in one direction, and those hitting in the southern hemisphere, albeit they call them, at least in Asia, monsoons, they're hitting it in the spinning in the opposite direction. And when they hit the shorelines, they hit them depending on which way they're going. So this is basically a similar phenomenon, except that these speeds are ridiculous. I mean, you're talking 500 kilometers per hour. This is tremendous speed. I mean, it's about what, 300 miles per hour? 300 miles per hour, that's a lot of wind, okay? So because the planets are big, although in this case, the weather in this case is big, so it needs a lot of force to move it, but again, you have a lot of mass to move that causes it to move and spiral. Again, this is the Great Red Spot. So, and this is a vortex that has formed a long, long time ago. At least it has been observed for over 300 years by Galileo himself when he took that toy and directed him there. And it's a big one. It takes about 3 Earths to fit inside one of this. And actually, and it's not unique to these regions of the planet. It's everywhere. There's all kinds of vortices that form. Okay, and including also on Saturn. Okay. But again, it has a lot of wind also, Saturn, and Cassini sent a lot of data, and so also the hexagonal, basically. There is like a hexagon that formed actually in its polar regions. And that is driven by the winds again. Okay, so again, the magnetic field, they have a lot of magnetic field, both the Jupiter and Saturn, and their magnetic field, they dwarf that of the Earth. Okay, and for the missions that takes us to these 2 planets, usually people are, astrophysicists and astronomers are extremely cautious with this magnetic field because they could destroy the instruments that you have on board. Okay, even if the instruments are, if they're just purely electrical, they could be really induce a lot of currents in them and cause damages to them. And because of that, they explore. They go through also auroras, especially for the case of Jupiter. I mean, this is actually a big event that can be observed. And actually, in the recent pictures from James Webb, it shows that actually in a very significant fashion. Okay. I know we still have another unit to discuss in this week, so I'm going to defer that to Wednesday when we meet again, and I'm going to post that to you guys, and also we'll have discussions. Let me check quickly on this week. Of course, you have your lunar observation that is actually due today for the second one. Let me make sure I have the information correctly here. By the way, you guys are receiving, I hope that you are, you have your notifications coming from Canvas on a regular basis of what's going on in terms of assignments and basically things like that. So it's due the second lunar observation. I'm looking actually at the issue. Here is the thing, because the lunar observation, yes, it starts from the week before, but then it's announced for the week later because of the fact that we had this switch. So let me look at the week 6 because it will tell me. So the lunar observation, the second one is due today, yes, October 17th. And you will receive a notification. I know, but by the time I upload this one, you would have received it already. For most of you who are not here, you would receive a notification today at noon. I'm looking at the announcements today, October, yes. At noon is just another reminder that you will have your lunar observation. So please take care of it. That's a very important part of your class, and document your observations. I know you were asked to go yesterday to do your planning for today's observations. You will have the third lunar observation next week. And then after that, there will be the last lunar observation, and the project can be assigned. I'm looking at other assignments in here. Of course, you have the discussions from week 6 and week 7, and you have a quiz that is due this Saturday, okay? In addition, and you have a homework assignment that is due, but it still has the 29th, so it's still kind of a little bit in the future. But we had that discussion for that homework last time when we went through it in a little bit more detail. If you guys think that you need more help, please let me know. Thank you.